facade renovation. Co-authors are Professor Ernesto Gambao and Professor Thomas Bock. The building renovation with modules, it's currently a hot topic, especially in Europe. The objective of this is to reduce the energy consumption of buildings by insulating the facades and also including some renewable energy sources. For that purpose, I determined 3 different subsystems. The first subsystem is data flow, which spans from data acquisition, design of the modules, and the data necessary for placing the modules accurately on its side. The second subsystem is the manufacturing offsite, the manufacturing of the modules. The goal is to have a 100% prefabricated element with no rework necessary on site. And the third subsystem is the on-site installation, which consists on all the process for installing the modules in its required place. I broke down this subsystem in some other subsystems as well, or subsystems, and I made an analysis of these broken down subsystems, and the parameters for analyzing were the time that is needed per square meter and per worker for a fully installation of the module, which includes data acquisition, for instance, design of the modules, manufacturing of the modules, and of course installation of the modules. The second parameter is manufacturing accuracy. So we can see that the higher time is needed for machining the elements and the precision of the elements, the higher accuracy we can gain, but as well the higher time is consumed for the manufacturing, for the installation of the whole module. So 4 different solutions were gathered to improve the time and the accuracy. The first solution consisted on defining automatically the layout of the modules only with the input of the point cloud. Currently, the point clouds, well, there is a way of processing them, but it's still time consuming, and it's difficult to determine the exact line of the primary layout of the modules. It's difficult to determine the criteria where to mark it, let's say. So for this purpose, some algorithms were created in Python, and in Dynamo, these algorithms were somehow compiled, and the solution was to determine the layout of the modules, as you can see on this video, which consisted on determining the perimeter, determining the line of the windows, the horizontal lines, also the lines of horizontal division of the modules, and the polygons of the modules as well. A test was created. Well, a test, or let's say, there was a proof of concept of this solution, and comparing to manual processes which are shown on black. Well, we can see that depending on the accuracy of the point cloud, we can gather a pretty accurate solution, or we can have major differences. Regarding time, of course, there is a huge time consumption comparing to manual processes. The second solution focuses on the manufacturing subsystem. Currently, the windows of a timber frame, for instance, timber frame module, are manufactured separately because they require more accuracy. That's why they need to be machined in a CNC. The rest of the elements are normally cut in a normal saw. That brings a manufacturing line based on two lines. The first line where the saw is, the profiles are cut, and on the line 2 of the workstation I, in this case, there is a CNC that machines the element on the window frame. There is the process in total takes about 0.165 hours per square meter. And well, I think the process could be improved in the sense of if machining all the elements of the timber frame, one might consider that it takes more time, but in the assembly process, it's much faster, I would say. For that purpose, well, a new manufacturing line was envisioned with only using the CNC machine, and some tests were accomplished, and the tests show higher accuracy, but also not considerable time reduction. Even more, if instead of one CNC machine there were two, the time reduction would be even bigger. So in this case, the company can check if the solution fits or not to their requirements. Solution 3 focuses on the installation process. The installation process has some problems because due to wind and other environment hazards like rain and whatsoever, it's difficult to position the module in its exact position. Therefore, we defined a cable-driven robot for the installation of curtain wall in this case. In the beginning, we were thinking on using this cable robot for building renovation, but some partners were more keen on using it for curtain wall and new buildings. But the problematic is mainly the same in this case, I would say. We need, for installing the curtain wall, we need to make holes, fix brackets, and install the modules on top of the brackets, as you can see on this picture. Once the crane is installed, the brackets can be fixed to the concrete slab, as you can see on this video. Once all the brackets are installed, we can install the curtain walls in its exact location. One of the burdens of this project, let's say, it was the excessive time used for installing the cable robot itself. The fourth solution consists on a solution for placing the connectors on the existing wall. As you can see here on red, the connectors need to fit. The connectors in blue and the connectors in red need to fit. The connectors in blue go to the module and the connectors in red go to the existing building. Where to fit these connectors very accurately? There are two problems. One is the unevenness of the existing facade. For instance, in such a small piece of wall, we have differences of more than 20 millimeters in a planar, so to say, wall. And the other problem is that even though we are using robotics and other technology, placing a bracket accurately might be difficult because there are some reasons that, well, apart from the unevenness, there might be rebars on the concrete and so on that might not facilitate exactly this process. Even manually, let's say, the operator needs to level the connector accurately. For instance, in 50 centimeters, we can find that there are 3 millimeters of difference on the wall. So the idea in this solution is to create more or less digitally these wedges or this kind of leveling interface. A test was accomplished. Here we can see the interface. And what we do is first we place this part 1 with certain accuracy, with certain tolerances, I would say. We measure this part, and once we know where this is, we can recreate the interface very accurately. We had measured these results, and the results were quite satisfactory. So we had 4 different solutions, but none of the solutions are a full, let's say, from start to the end. They are not a full solution by themselves. So that's why in this paper, 3 combinations are explained. 3 combinations by combining the aforementioned 4 solutions. And we can see that there is a time reduction comparing to the analyzed cases. But the time by itself is not the only proper parameter. We need to calculate also the accuracy of the solutions. Therefore, by using some other calculations, the combination, each of the combinations was also somehow assessed in regard of the accuracy. Nevertheless, there are still some future needs that need to be fulfilled. So therefore, there is also in the paper, you can find a list of future needs that need to be, or it would be interesting if they are accomplished sometimes. So future researchers, companies, and so on, with this paper, they might know where these future needs are, as I'm commenting here in the conclusions. These are the references I used, and thank you for